Dear students, welcome to our course Mathematical Methods. We now study the second module in Unit 4 entitled Taylor Series. The learning objectives of this module are to study the Taylor series expansion of a given function about a given point, to study the Maclaurin series expansion of a given function as a special case of the Taylor series expansion, to study the radius of convergence and circle of convergence of the Taylor's and Maclaurin series expansion, and we can practice the related problems. So now the Taylor series expansion of a function about a given point. So we have studied that every power series with a non-zero radius of convergence defines an analytic function. Note that the converse of this result is also true. That is, every function f of z which is analytic throughout a disk can be expressed as a power series which converges to the function f of z inside the disk. Such a power series is called Taylor series, which was stated as follows. Suppose that a function f of z is analytic throughout a disk, mod of z minus z naught is less than or centered at z naught with radius capital R. Then f of z has the power series representation as f of z is equal to summation of an times z minus z naught whole to the power of n, where summation runs from 0 to infinity, defined over the disk. Mod of z minus z naught is less than, or where an is defined as nth derivative of f at z naught divided by n factorial, where n runs from 0, 1 to and so on. That is, the series 1 converges to f of z when z lies in the above stated open disk. Now we will learn some important notes on this Taylor series. The power series 1 is the familiar Taylor series from the calculus adapted to the functions of a complex variable, with the agreement that 0th derivative of f at z naught is equal to f of z naught and 0 factorial is equal to 1. Then we can express the above Taylor series as follows. F of z is equal to f of z naught plus f dash of z naught by 1 factorial times z minus z naught plus f double dash of z naught by 2 factorial times z minus z naught whole square, plus and so on, nth derivative of f at z naught by n factorial times z minus z naught whole to the power of n, and so on. So any function f of z which is analytic at a point z naught must have a Taylor series about z naught. If the function f of z is not analytic at a point z naught, then it cannot be expanded in Taylor series about the point z naught. This is very important. Since the Taylor series representation of an analytic function is always unique, so we can also obtain this expansion directly by using binomial series expansions whenever it is possible. And if f of z is analytic at a point z naught, then it is analytic throughout some neighborhood. Mod of z minus z naught is less than delta. We call delta neighborhood of that point. And hence we notice that this delta serves as the value of the radius of convergence capital R in the statement of the Taylor's theorem. That is, if f of z is an entire function, then the radius of convergence is R is equal to infinity. Since f is analytic on the entire finite complex plane, and the condition of validity becomes mod of z minus z naught is less than infinity. Thus, the series converges to f of z at each point z in the entire finite complex plane. And the final point to notice from the Taylor series is, if f of z is analytic everywhere inside a circle of convergence capital C centered at the z0, then the convergence of its Taylor series about z0 to f of z for each point z within that C is ensured, and even no test is required to test the convergence of the series. That gives the guarantee by the Taylor series. If the function is analytic everywhere inside a circle of convergence. So that according to the Taylor's theorem, the series converges to f of z within C whose radius, please remember this point very carefully, my dear students, whose radius is the distance from z0 to the nearest point z1 at which f fails to be analytic. That means the radius of convergence can be calculated as the distance from the point z0 where the function is analytic to the nearest point z1 where the function is not analytic. So now let us see an example based on this Taylor series. Expand the function f of z is equal to 1 by z about z is equal to 2 in Taylor series. Obtain its radius of convergence and circle of convergence. Let us see the solution, guys. By Taylor series we have, what we have? F of z is equal to summation of a n z minus z naught whole to the power of n mod of z minus z naught is less than or, where a n can be written as nth derivative of f at z naught by n factorial, where n is equal to 0, 1, 2 and so on. Now given the function f of z is equal to 1 by z and z naught is equal to 2. Now we can notice here the function f of z is analytic everywhere except at the point z is equal to 0. That means notice that the function f of z is equal to 1 by z is an analytic function about the point z0 is equal to 2, and hence we can obtain a Taylor series expansion for f of z about the point z0 is equal to 2. That means we are confining that the function f of z is equal to 1 by z is analytic at the given point z0 is equal to 2, so that we have the Taylor series expansion. Now substituting the things in f of z in the Taylor's expansion, then we have this summation of a n times z minus z0 is 2 whole to the power of n mod of z minus 2 is less than or, where a n is equal to nth derivative of f at the point z0 which is 2 by n factorial, where n is equal to 0, 1, 2 and so on. So now f of z is equal to 1 by z, then a0 is equal to f of 2 which is 1 by 2, and the first derivative of f is minus 1 by z square, and a1 is equal to f dash of 2 by 1 factorial which is minus 1 by 2 square, and the double derivative was calculated and a2 was calculated as 1 by 2 cube. So third derivative of f at z is minus 6 by z power 4, and a3 was calculated as minus 1 by 2 power 4. So by observing all these things we have a0 is 1 by 2, a1 is minus 1 times 1 by 2 square. I am arranging like this to find the an. a2 is equal to minus 1 whole square 1 by 2 square. a3 is equal to minus 1 whole cube times 1 by 2 power 4 and so on. My dear students, can you guess what is the nth term here? Observe the pattern carefully and guess what is an. Yes, an is minus 1 whole to the power of n times 1 by 2 power n plus 1. Now substitute everything in the above f of z, Taylor's expansion, what we have. Thus we obtain the Taylor series f of z is equal to 1 by z is equal to 1 by 2 minus 1 by 2 square times z minus 2 plus 1 by 2 cube times z minus 3 whole cube minus and so on, minus 1 whole to the power of n by 2 power n plus 1 times z minus 2 whole to the power of n and so on. By putting it in a summation format, we have this summation of minus 1 whole to the power of n by 2 power n plus 1 times z minus 2 whole to the power of n, and where an is minus 1 whole to the power of n times 1 by 2 power n plus 1, where n runs from 1, 2 and so on. So here the n runs from 0, 1, 2 and so on. Now we can find the radius of convergence and the circle of convergence. In the earlier module we have utilized the ratio test to find the radius of convergence and the circle of convergence. So now we have mod of an by an plus 1. So I have an over there and an plus 1 I have written like that. Then simplify the calculation, my dear students. What you will get? Try yourself. Yes, it is 2. Therefore, the radius of convergence r is equal to limit of n tends to infinity mod of an by an plus 1 is equal to limit of n tends to infinity, which is 2. So since 2 is a constant, we get the limit value as 2. Therefore, the radius of convergence is r is equal to 2 and the circle of convergence is mod of z minus 2 is less than 2. Now we have computed the Taylor's expansion for the given function about the point z0 is equal to 2, and we have the radius of convergence and the circle of convergence. So we have already noted that point. Since the Taylor's expansion is unique, so that we can find the Taylor series by utilizing some binomial series expansions whenever it is possible. So I am trying to find out the Taylor series in that manner by utilizing the binomial series. So since the Taylor series representation of an analytic function is unique and f of z is equal to 1 by z is analytic about the point z0 is equal to 2, so we can obtain the series expansion as follows. I have this f of z is equal to 1 by z. I am writing that 1 by z, denominator z can be written like that, and I am arranging in that format. Please observe it, is it right? 1 by 2 times of 1 plus z minus 2 by 2 whole power minus 1. So in PUC we have studied the binomial expansion 1 plus x whole to the power of minus 1. Can you remember, guys? See the expansion. 1 plus z whole to the power of minus 1 is equal to 1 minus z plus z square minus z cube plus and so on, minus 1 whole to the power of n, z power n and so on, which can be written in the summation format, summation of minus 1 whole to the power of n z power n, where mod z is less than 1 and radius of convergence is also 1. By utilizing this expansion, I am expanding the things. 1 by 2 times minus 1 by 2 square z minus 2 plus 1 by 2 cube times z minus 3 whole square. That is 1 by 2 cube times z minus 2 whole square minus and so on, minus 1 whole to the power of n by 2 power n plus 1 times z minus 2 whole to the power of n plus and so on. There is a topographical error. 1 by 2 cube times z minus 2 whole square. So which is converges when mod of z minus 2 by 2 which is less than 1, that is mod of z minus 2 is less than 2. Thus we have the radius of convergence is 2 and the circle of convergence is mod of z minus 2 is less than 2. Therefore we have the Taylor's expansion for the function f of z is equal to 1 by z is that, and where an is equal to minus 1 whole to the power of n times 1 by 2 power n plus 1, where n runs from 1 to and so on. Now we can recall some of the binomial expansions which are very useful in computing the Taylor series expansions. The following are some of the binomial expansions which are repeatedly useful while computing the Taylor series expansions. So these are the things, and 1 minus z whole to the power of minus 1, which is summation of z power n, whose radius of convergence is 1 and it is valid on mod z is less than 1. Similarly, 1 minus z whole to the power of minus 2, we have summation of n plus 1 times z power n, radius of convergence is 1 and mod z is less than 1. 1 plus z whole to the power of minus 2, which is summation of minus 1 whole power n times n plus 1 times z power n, radius of convergence is 1 and circle of convergence mod z is less than 1. Now we will study what is a Maclaurin series. So Maclaurin series expansion of a given function. We can deduce this Maclaurin series expansion from the Taylor series. Let us recall the Taylor series expansion of the function f of z about the given point. So this is the things. And substituting z naught is equal to 0 in this Taylor's expansion, what we get? Let us substitute, my dear students. So z minus z naught is 0. That means an times z power n. And you will get mod of z minus z naught is less than or, means substituting z naught is equal to 0, you will get mod z is less than or. And an is nth derivative of f at 0 by n factorial, where n runs from 0, 1 and 2 and so on. That is f of z is equal to summation of an times z power n, mod z is less than or, where an is nth derivative of f at 0 by n factorial, where n is equal to 0, 1, 2 and so on. Notice that this is called Maclaurin series expansion. The above series is called Maclaurin series expansion. So like the Taylor series, Maclaurin series expansion is also unique, and we can also obtain this expansion directly by utilizing some binomial series expansions whenever it is possible. So notice that Maclaurin series representation of an analytic function is also unique, which we can also obtain this expansion directly by utilizing the binomial series expansions whenever it is possible. So let us see an example, guys. Obtain the Maclaurin series expansion of the function f of z is 1 by z square plus 1 plus 2i times z plus 2i. Find its radius of convergence and circle of convergence. Let us we can calculate. So by Maclaurin series, what we have? This is the expansion. Now I am writing the given function f of z as like this, product of the factors, and I am taking 1 by 1 minus 2i as common, and multiplying with that I can make the partial decomposition, partial fractions. So observe carefully, my dear guys. Now notice that the function f of z is analytic for all z except at the points z is equal to minus 1 and minus 2i. Thus f of z is analytic at z is equal to 0. Since the Maclaurin series representation of an analytic function is unique, so we can obtain the expansion of f of z directly by using the binomial series expansions. So we have these things, and I am manipulating 1 by z plus 2i binomial series expansions. I am rearranging that 1 by 2i times 1 plus z by 2i whole to the power of minus 1, whose binomial expansion is like that, and which is valid on mod of z by 2i is less than 1, that is mod z is less than 2. How you are getting that mod z is less than 2? Mod of 2i is always 2, so that mod z is less than 2. Therefore, the radius of convergence of the above expansion is R1 is equal to 2 and the circle of convergence is mod z is less than 2. Similarly, you can obtain for the second one 1 by z plus 1, which is very simple. 1 plus z whole to the power of minus 1. We can write minus 1 whole to the power of n z power n, which is valid for mod z is less than 1 and radius of convergence is also 1. Therefore, radius of convergence is R2 is equal to 1 and the circle of convergence is mod z is less than 1. Please remember, the radius of convergence of the first term is 2 and the second one is 1. R1 is equal to 2 and R2 is equal to 1. Please remember, guys. So, hence f of z can be written as, and we are substituting all the Taylor's expansions of the first one and second one, and by simplifying this we are getting the Maclaurin series expansion of the given function. So for Maclaurin series we can take the point z0 is equal to 0. So now the radius of convergence of the entire function f of z is, in the earlier module we have studied that the radius of convergence is minimum of R1, R2. That means sum of two series or difference of two series or product of two series. If the series are having the radius of convergences R1 and R2, then you can take the sum of or difference or product of the two expansions will be minimum of R1, R2. Therefore, here the radius of convergence of the function f of z will be R is equal to minimum of R1, R2, which is minimum of 2, 1, which is 1. That means which is the distance between the point z is equal to 0 and the nearest point z is equal to 1 at which the function f of z is not analytic. In this way also we can find the radius of convergence of the given function. That means the distance from the point where the function is analytic to the point where the function is not analytic. In that way also we can find the radius of convergence of the given function. And the circle of convergence is mod z is equal to 1. Now we can see the Maclaurin series expansions which are useful in manipulating the Maclaurin series expansions of the given functions. So these are the very standard functions and whose Maclaurin's expansions are given here. Please learn properly and remember those things to compute the Maclaurin's expansions for the given functions, which are e power z, sin z, cos z, ln of 1 plus z, and their corresponding radius of convergence and circle of convergence. So we are come to the end of the module, my dear students. Please go through the material which we have provided to you and learn the problems properly. Thank you. Thank you so much.